Here I will present another test case, so test case 2, related to the set membership approach for SLAM simultaneous localization and mapping of a robot moving inside an unknown environment. So let me start. Here it is a trajectory of the robot, so envelope of the trajectory that can be determined using the differential equation. The robot is moving as represented here. It is its initial position and it is a current position. Around you have obstacles represented here, unknown obstacles. The only thing the robot can measure, it is the distance between its position to the nearest obstacle. So it will finish inside the triangle. When it is moving, it is able to dig the space, and it knows that here you have nothing. In the gray area you have nothing. He has no idea of what there exists inside the white area. So using what has been dug here, it was able to remove some inconsistent value of its trajectory represented here. So here I represented parts that have been contracted using the consistency with the inner map. Then the iteration starts again. So since the robot has a better approximation where it is able to dig with a better approximation the space. That's why thinner is the envelope here, then bigger will be the dug space. So we hope that it will converge to the actual map. Of course it will not be the case, but we would like, in ideal situation, that the gray area converge to the free space of the room. So now the robot is soon at the end, and it continues, so it becomes quite lost here. This picture represents the uncertainty. So at the beginning the robot knows where it is. At the end, so here of course this envelope decreases, so it becomes better and better. So here it is the accuracy that the robot has at the end. So the robot's finished, and then he starts again removing boxes here, boxes that are in black, that are inconsistent with what has been dug. So of course it will propagate this uncertainty using the state equation of the robot. So here, as we can see, when we are able to contract, then for some k the error becomes smaller, but for only few k's, of course it will be smooth using the differential equation. As we can see here, quick, here in the forward and backward linear. Yeah. So dark gray is a backward approximation, and white gray was the forward approximation. So now we know that everything that are in the light gray have been removed. We know that the robot has moved inside the dark gray area, and it starts again. Then we hope that the robot, of course, will have a convergence. And here we can see what happened at the beginning. The approximation is bad, and then the approximation becomes better and better. The inner approximation increased also. And let me show at the end. So I hope I will decrease here. Come on. And at the end will converge to a quite thin envelope, and here the dug space is almost corresponds to the free space. Of course it was not able to connect some places, there is still some white zones, also uncertain white zone, but the approximation is quite good. So as we can see here, it is the error of the position of the robot with respect to time. So at the beginning it is a simple line, and after it decreases, and at the end we see that, of course, at the beginning it is better, but now we can see that with respect to time the error is almost constant. So the robot is never lost.